Hello, everyone. I am Dr. Asterius Leonidas, a postdoctoral researcher at the Institute of Computer Science of the Foundation for Research and Technology Hellas. This presentation will focus on Task 4.3, titled Large-Scale Biometric Data Indexing. Before diving into the technical details of the module, allow me to emphasize the essential need for this component. Let's consider a scenario where a crime has occurred, but regrettably, the suspect managed to escape, and no physical evidence, such as fingerprints, could be collected at the scene. Fortunately, the security surveillance system recorded a brief video clip of the criminal in motion and captured some photographs of the individual. However, despite the close-up footage captured by the surveillance system, the individual remains unidentified to the authorities. He is essentially a John Doe, a face without a known identity. To identify him, authorities would need to manually search through thousands of images of hundreds of suspects. To identify potential individuals who could be matches. Apparently, this is a very tedious and error-prone task, as a human operator must sift through numerous images to find similar ones. The objective of this task is to address this challenge by enabling efficient biometric data indexing and searching at scale. Therefore, it will empower practitioners, such as law enforcement authorities and institutes, to conduct faster identity matching of a biometric sample, even in cases where the data are distributed, for example, in a cross-border scenario where multiple databases need to be searched. TENSOR's technical implementation of large-scale biometric data indexing utilizes advanced deep hashing techniques for approximate nearest neighbor search, enabling rapid and efficient retrieval of large-scale biometric data, with a particular focus on facial images. This approach effectively tackles the high dimensionality of biometric data, maintaining differentiability properties and grouping similar data. As a result, it minimizes computational costs and boosts the overall effectiveness of the search process. In a nutshell, the model accepts an image, in TENSOR's case, a facial image, as input and transforms it into a vectorial representation, aka a hashcode, significantly reducing its size. This hashcode can be stored in a database, facilitating efficient searches among the indexed images. When a new, unknown image is presented as a query, it can be searched against the entire collection using the stored hashcodes. The module operates in three distinct phases. In the initial phase, known as the model training phase, which occurs offline, the deep learning indexer undergoes intensive training using an annotated, high-quality, and relevant dataset. This training is essential to equip the module with the intelligence required to understand and categorize complex patterns within the data. Next, once trained, the deep learning indexer is deployed across multiple instances, in every LEA's private space, in a distributed manner. Its primary objective is to crawl and extract information from local authority data sources, and transform that information into hashcodes that can be searched. These information are stored locally in every LEA's private data pod and are not distributed online. In essence, at this phase the catalog of the database of suspects of its LEA is produced, in an optimized and secure way. In the final phase, the live operation, human operators, using a straightforward user interface, request the system to search for suspects similar to the one provided as input. The central comparator module, after converting the image of the suspect into a vector, hashcode, securely forwards this information to the distributed local comparators, along with a request to find the top k most similar images/suspects. As the responses accumulate, the central comparator assumes the role of data aggregation and presents, through the user interface, appropriately annotated results indicating the number of matches found across all databases. The input data for this module consists of close-up face images. This data is utilized during the training phase to configure the deep learning component to identify images of this specific type, i.e., close-up faces, and during the indexing phase where the provided data are being indexed. During execution, the module takes a face image as an input parameter and outputs the top k-ordered images similar to the input. Currently, the model is being trained using an aggregation of two different public datasets, namely the YouTube Face and Face Scrub, featuring over 2,100 individuals. In this slide, you can see an example of the module's output. Given the single image on the left, in particular an image of Alan Rickman, the system returns the top 10 images that are most similar to the input. In this specific example, all 10 images correctly belong to the same individual. This is another example where the list of the top 10 most similar images, compared to the one on the left, belonging to Alice Krieger, incorrectly includes two images of another individual, namely Jamie Luna. The large-scale biometric data indexing module will play a crucial role in use case 3, enabling LEAs to initiate queries for biometric data analysis. This will enhance investigative efforts through a user-friendly interface that generates easily comprehensible data for effective analysis. Furthermore, the module is expected to provide relevant evidence to forensic institutions for match verification. It will establish cross-border connections to identify potential matches, promoting information sharing by enabling simultaneous searches across multiple databases. This facilitates efficient collaboration among investigators and international counterparts, allowing them to review evidence and case details. The module's architecture prioritizes data protection and confidentiality. Communication with forensic experts and international partners ensures that indexed images reside securely within each LEA's private space. The only data exchanged is an encrypted hashcode of the suspect. Subsequent communication upon receiving results will adhere to the specifications outlined in the TENSOR platform. Through the initial screen of the similarity search tool, users can choose the images for which they want to find similar ones. Previously uploaded images are accessible for users to select from. Additionally, users have the capability to upload new images to the system by browsing through their files. The use of a shopping cart metaphor allows users to search for similar content for multiple images simultaneously. Upon clicking on an image, it is promptly added to the list of images intended for analysis. To address potential errors, users also have the option to remove images from this list. Once the user is ready, they can instruct the tool to locate similar images. After the completion of the search process, users can examine, for each input image, the top 10 similar images. Thank you for your attention.